Hi, I'm Lucas, one of the co-founders of Knowunity, and we are building an AI learning companion for students. Currently have around 1 million daily active users on the platform, and today I would like to tell you the story of how we've been building Knowunity, and especially our AI learning companion. Maybe to quickly give you a bit of background first. We basically had the idea for Knowunity around 6 years ago when we were still in high school, and back then noticed that there was no real platform for students to be able to study together. School didn't really feel fun for any student. It felt always super uninspiring. Students didn't really like going to school. And especially, it didn't really feel personal. So we had a strong conviction that we had to change something about it. And especially nowadays with AI, this has been a no-brainer for us that education is one of these spaces that will benefit the most positively from everything that is happening in education, especially since already nowadays every student is able to have their own personal tutor in their pocket that is with them at all times, that's never getting tired of them asking the same question 10 different times in a row, that's always there for them, knows exactly how they study in the best personal way. And that's why we have the mission of building the all-in-one platform for students where they get personalized help, be it for exam preparation, be it for homework, be it for revising and practicing, everything in one platform, supported by around 3 million content pieces that have been uploaded by students that help us ground the answers and therefore give students better answers. Under the hood, for us, always the big question is how do we give the students the best possible answer? And for that, we don't just have one path of how we answer our students. Instead, we do LLM routing. So every incoming request in the first step gets classified. So we take a look at what intent does the user currently have. We check the complexity of the question. If it's a more difficult question, such as a difficult math question, we go for a stronger model. Whereas if a student asks a very basic definition question, we are able to leverage a small model, especially since we are mainly working with high school students. And high school students have a rather low attention span, and if they have to wait for an answer for too long, they tend to drop out quite quickly. We also check what kind of attachments would make sense, study sheets, quizzes, mock exam, flashcards, to basically make the whole experience more engaging, and also attach every single incoming message and interaction to our knowledge graph to be able to figure out what is the student currently talking about, and therefore map the whole curriculum for every single cohort on a region and a grade level for each country, and therefore able to figure out what is the student currently talking about. And based on these data points, we then decide what system prompt are we going to use, what tool calls do we inject into the LLM, what model are we actually going to use, what model parameters do we set, so how much thinking do we allow the model to do, how creative should the model be in terms of what temperature is it going to use, but also how is the visual flow going to look like. And for those classifications, we've gone through a journey of different iterations. In the beginning, we were just using LLMs directly to do classifications. The big advantage here was that it was super easy to get started. It's super easy to iterate. It's just a prompt in the end that needs to be adjusted. But it's not as accurate as we need them to be, especially when it comes to small nuances that the LLM doesn't always fetch properly. We then later on switched to AutoML classification models, mainly with the motivation to reduce the latency. Since I said students have a low attention span, so we always need to make sure that we get the time to first token as low as possible. And also because AutoML classification models have been quite cheap and easy to work with, but still less accurate compared to LLMs, since in other cases, for example, if the student is having a long conversation, is switching topics a couple of times throughout the conversation, the smaller AutoML classification models, they were getting quite confused about the context and about the order, what to focus on. So nowadays, we are mainly leveraging fine-tuned LLMs for classification. They basically combine the advantages of both of them. They are quite low in latency, quite low in costs, but have the ability to catch nuances and are still a bit more effort, yes, to iterate on, since it's not just a prompt that needs to be adapted, but also a whole data set that needs to be maintained. But over the last couple of months, it has become way easier to maintain those data sets because we are also obviously leveraging LLMs. And if 3 very strong LLMs agree on the label, then it's very likely that it's correct. And then we, as humans, only need to double check the cases where 3 LLMs disagree, and those are then the interesting cases where we can, as humans, still help the LLM to take better decisions. One other category of classifications is, as said, our classification for our knowledge graph. So every incoming message gets classified for us to be able to figure out what is the student currently talking about. And the big difficulty here is that we have a lot of classes. So per cohort, there are around 10K different topics that a student might be studying. And that's just very hard to fine-tune an LLM for each different cohort and to iterate quickly on there. So here we are mainly using vector search, so every incoming message is being embedded, and then on the other side we also embed the topic using a hypothetical document, and by matching those 2 together and checking how similar they are, plus using an LLM to re-rank the results, we're able to figure out quite well what the student is currently talking about, to then be able to inject context that is specific to that topic. For example, what conversations did the student have about the same topic in the past, how has the student been struggling with the topic, and also how other students have been studying the same topic. One quite important part for us is obviously always the quality of our AI companion, making sure that we both give factually correct answers, but also making sure that we give answers that are engaging, that have the right tone of voice, that we show the right visuals and the right attachments in the right moment. And therefore, we build up a continuous feedback loop that allows us to some extent to autonomously improve the quality of our companion by combining a couple of different feedback sources, very basic ones like the student being able to upvote and downvote messages, LLMs as a judge that on a daily basis take a look at a couple of thousand messages and conversations to check what kind of typical issues we've been seeing, but also things like sentiment classification and other types of reports that then go into our so-called quality observer, which is basically running on top of Cloud Code and is trying to figure out typical issues that students might be facing, is then coming up with hypotheses how it could resolve those issues, be it sometimes simple things just as introducing a new model for one path of our routing engine, sometimes also rewriting the whole flow, changing the system prompt. And once it found an hypothesis that it might be worth trying out, it then automatically runs an offline evaluation against our data sets, against our offline data sets, to check whether the hypothesis does hold true, at least in the offline scenario. And if it does, it sends a message to a Slack channel for an engineer to double check it. And even though we do have quite high trust in our offline evaluation data sets, we still like to double check with our users and double check what impact those changes actually have on our users. And therefore, we're running a lot of A/B tests. A/B test is basically for us the #1 way of how we improve our product, both be it when it comes to how the UI is changing, new features that we introduce, but also system prompt changes, routing changes, and model changes. Every single change is being A/B tested for us to see what impact they have in the end on our users and on main product metrics. Very important for us here is also that we want to be able to iterate as quickly as possible on the product. So therefore, we've invested quite a bit into the infrastructure, making it as easy as possible for us to run experiments, both for engineers but also for agents, making it as easy as possible to evaluate experiments, generate learnings from the experiments, and with that feedback loop, now manage to run around 30 to 40 different experiments per week. Given that there are 1 million students on a daily basis that use the app, we're able to quite quickly also get statistical significance and therefore iterate on the product and improve it over time. One other quite unique thing is that we have a lot of content from students on the platform. It is true that LLMs by now, they have all the basic knowledge. Every LLM out there knows how to define photosynthesis, but still there are quite a lot of areas where LLMs might not have the right knowledge, especially, for example, when it comes to literature. Most LLMs don't really know what students would find on page 20 of a specific book that's read in Romania. And therefore, by injecting those content pieces into the context of the LLM, we are able to improve the accuracy of our answers, but also adapt the difficulty and the wording of the answers. Since if you think about a student that in grade 5 in Bavaria, for example, they would learn a topic in a different way compared to a student in grade 8 in Berlin or in any other country out there in the world. So therefore, by injecting those content pieces, we allow the LLM to figure out on what level is the student supposed to learn the topic, what kind of wording does the school typically use around the concept that they are currently learning, and therefore make it easier for students to grasp the answer and get them not less confused about it. Plus, we are also using those visual content pieces to make the answers more engaging by, for example, injecting stickers into the answers, by allowing students to dive deeper into the answers, and therefore not just having a wall of text, but allowing the students to have a more engaging experience in the end. Personalization, as mentioned in the beginning, is also quite relevant for us in the sense that if you, for example, think back to your own time at school, in school you typically have a class with one teacher and 30 different students, and every single student is unique, which then always leads to some students falling behind, some students being a bit ahead, but the teacher just not being able to focus on the individual student. And therefore we've invested quite a bit into making sure that we learn as much as possible about the students, figure out what are their preferences, what are their learning styles, how have they been progressing in the past, where they're weak in, where are they strong already, and then based on that, figuring out what kind of preferences do they have on a user level. For example, a student might be interested in football, and therefore we in all subjects always give them examples about football. Then we figure out that in, for example, math, they like to learn with mock exams, so we record that preference only for one subject, and then have preferences and memory also on a topic level. For example, the fact that a student has been struggling with one topic is then being stored and injected if the student is talking again about the same topic. One challenge that we've been facing is, given that we have a lot of users on the platform, we need to process quite a lot of tokens and need to do that in a reliable way. And students have a very typical study pattern. Most students, when they come back from school, they do homework, they do study, and therefore we have big peaks in the afternoon when a lot of students want to use the platform at the same time. And on the flip side, there is obviously a big lack in compute, and most of the LLM providers that we are leveraging, they also face a lack in compute and are not as reliable as we would need them to be. So therefore we had to invest quite a bit into different mechanisms of how we can improve the reliability. For example, by leveraging fallback ladders. So when an engineer writes a prompt, they don't just write it for one single model. They have one preferred model that they define, but they then also define a set of fallback models so that we are easily able to fall back to another model in case the main model is not available. We also try to make sure that every model that we use, we have at least 2 providers available, so that in case, for example, the model is currently slower on OpenAI, we're able to fall back easily to Azure or OpenAI, and vice versa, to make sure that we're able to use the best model in that moment. One other technique that we're using for very high priority use cases is that we are doing request hedging, where we basically send a request twice and check which LLM provider is faster, and then basically use the faster one. But obviously this is quite a bit more expensive, since even though the LLM provider might not give you back an answer because it's slower and we cancel the request beforehand, it still charges you for the request. So we're only using that technique for very high priority users, where we really need to make sure that we keep the latency and the reliability as good as possible. Another technique that we are leveraging is circuit breaking. So basically, we at all times monitor and check what LLM providers are currently less reliable, what models are currently facing higher latencies, and based on that, dynamically reroute the traffic. So in case, for example, we see that one provider is down, we temporarily take it out of the routing, keep sending a very small number of requests to be able to figure out when the provider comes back up and is more reliable, but in the meantime send more requests to other providers to make sure that students experience the best, have the best experience and don't have too long waiting times, and therefore drop out in those cases. All of that is supported by our AI gateway. We quite early on decided to build our own AI gateway, mainly because back then when we started, there were not yet that many AI gateway providers, and still also the main AI gateway providers that are out there right now, they don't 100% serve the reliability and fallback mechanisms that we need to be able to serve our users in the most reliable way. Plus, we also like to very quickly experiment with new models, like to experiment with new parameters right as they come out. And by having our own AI gateway, we're able to both serve our users in a more reliable way, but also make sure that we're able to use the latest and greatest features that LLM providers offer for us. Plus, it allows us to very easily make changes, since the AI gateway basically has one unified interface for all different types of models and providers, and therefore engineers just need to work with that one interface and don't need to think about how that request would now look like if it's sent to another provider in case of a fallback. To be able to improve reliability over time and also to improve the product, we also build up observability. Observability for us is actually, it looks quite simple. We decided to put all of our traces into BigQuery and not leverage an out-of-the-box LLM observability platform, mainly because we already have all of our product data in BigQuery, and therefore are very easily able to join the data from our product data warehouse with the data that we have in our LLM request history, and therefore figure out, for example, what impact does it have on retention if we do more fallbacks, what impact does it have on users in case we experience higher latencies, in case we do more thinking, and therefore very easily combine the data points to do more in-depth analysis. On top of the BigQuery table, we are then using a dbt model to extract all sorts of data points from the traces, be it costs, be it amount of tokens that were used, to be able to drive those analysis in an easy way. Plus have a small web app on top of the BigQuery table that allows engineers to visualize how much time was taken on the different steps of the request, allow engineers to dive deep into the prompt, figure out what kind of parameters have been sent, but also directly there are able to change the prompt, make adjustments to then see what impact it has on the users and on the final output to be able to get the most out of the LLMs. Good, and with that we're coming to an end. Thank you so much.